Okay, let's talk now about dynamic programming. It's probably something that you've seen in a data structures class before, but it's a tricky concept, and so even if you've seen it, we could all use a refresher. So this is a way of saving computation for recursive problems whose subproblems are number one, independent, and number two, overlapping. Okay, so if you have these two conditions in your recursive formulation, then you can use dynamic programming to memorize stuff and save computation. So we're going to use dynamic programming to memorize the subproblems. So the simplest non-trivial example I can start with is the Fibonacci numbers. So it starts off as 1, 1, that's the base case. And if n is greater than 2, so after the first two numbers, then the recursion kicks in. So I'll say Fibonacci of n, or the result is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. And then I'll return the result. Now, let me go ahead and maybe I'll add a variable here to say how deep I am in the recursion. And what I'll do is I will print out some information about the problem that I'm looking at. And I'll tab it over based on how deep I am. Okay, so let's see if I did the Fibonacci of 4. So here's what I have to compute. Fibonacci of 4 depends on Fibonacci 3 and 2. Fibonacci 3 depends on 2 and 1. And these are base cases. Let's do 6. Let's go a little further. So here's all the problems that I had to compute. In order to do Fibonacci of 6, I needed 5 and 4. In order to do 5, I needed 4 and 3. Now what we're starting to notice here is these overlapping subproblems. So in order to compute fib of 6, I needed fib of 5 and fib of 4. Let's say that I finished fib of 4 down here. Well, I don't need to do it again. I can remember it and cut it out. Now, one way to do this is just to have a dictionary that remembers things, the arguments that you called it with. That would be a top-down approach. So I would remember the solution to n if I hadn't seen it before. But I actually want to do a bottom-up approach instead. So dynamic programming assembles solutions from the bottom up. So if we have independent and overlapping subproblems, which we do, okay, so I showed certainly that they're overlapping. They're independent because the answer to this subproblem doesn't influence the answer to this subproblem, and the way that I assemble them doesn't matter. Like, I can answer this independently of adding them together. So if that's true, I can actually assemble the solution from the bottom up. So what I can do is make a little memory. Maybe I'll start it off as just all ones. And I'll start right past my base case. I'll say for I in range, so I start at 3 actually. 3 up to n inclusive. What I can say is, all right, I can use, so by the time I start here, I already have the solution to the two base cases. So I can say mem at index I is equal to mem at index I minus 1 plus mem at index I minus 2. And then return the last element there. So if I compare the two, so before I said fib of 6, that was 8. Let's just check this. Fib of 9 of 6. I meant to say mem here. And I should also be careful. I'm 1 indexing the Fibonacci numbers, but I'm 0 indexing the problem instances. It's a bit annoying. Maybe I'll just put a little dummy thing in front here. Okay. Anyway, good. So what I'm making sure of is that I've always computed the subproblems I need before I use them, right? So mem I minus 1 and mem I minus 2 are always finished before I need them to fill in this. So it's a way of doing recursion from the bottom up. and it uses usually some kind of array or way of organizing the subproblems in a convenient way. Okay. So I want to just go up a level of complexity with the kind of programs that we can look at here. And I want to talk about something called dynamic time warping. It sounds scary, but it's actually not. It's just dynamic programming applied to shifting things around in time, speeding things up and slowing them up. So let's say that I was running a race and Usain Bolt was running the race. And I take samples of where I am along the track at different times. So at time 1, I'm here. At time 1, Usain Bolt is here. Okay, so he's going a little faster than me, but we're running along the same track. And so I might ask you to actually line us up on the track regardless of where it happened. So for me, it would be time 2 to his time 1. See that? So what I can define is something called a warping path, which is a way of aligning, coming up with a correspondence from my time instance to Usain Bolt's time instances, so that we're always either staying still or moving forward by one place. We both start at the same one and we both end at the same one. And so just to show you, here's all the possible warping paths that I could create between us. So we're each either staying still or moving forward by one. Sometimes we could both move forward. And my goal here is to minimize the sum of the distances along the warping path. So you see, this warping path isn't quite as good as one that I'll get a little later. So here's the total cost when I sum up all these distances here. And it looks like, let's see, we might have to wait until we start over, but yeah, actually here's the best warping path that I could get. So the sum of these distances is very small. So if Usain Bolt just stays still once, waits for me, then we can both move along at the same time. So that's a very brief overview of something called dynamic time warping. Now, for dynamic time warping, if we let's let Sij be the best or the lowest cost I can get over all warping paths that align the first I points of the first time series. So time series, just a sequence of things. So the first I points of the first time series to the first J points of the second time series. So I'm going to define this thing called Sij, which tells me the best I can do out of the first I points in the first sequence and the first J points in the second sequence. Then I claim that Sij satisfies the following recurrence. So what we have is that Sij is equal to this kind of little expression. Getting a little fancy with the LaTeX here. But it's going to be Si minus 1 J. Well, I guess I only need one column here. It's the minimum between Si minus 1 J, Si J minus 1, and Si minus 1 J minus 1. Okay, so we have the min over these three plus the distance between the ith point in the first time series, maybe we'll call it the first time series X, and the jth point in the second time series. Okay, so that's the recurrence. Now this is also a case where we have independent and overlapping subproblems. Some of you may recognize this as a very similar kind of recurrence to the edit distance that we did in data structures before. But, okay, but in the abstract here, I'm just going to state this, and I'm going to tell you that this is true. We can prove it. But we'll just take it as a given for now. And what I'll do is use this to define a very efficient dynamic programming solution to the dynamic time working problem. So let's say I have two time series x and y. And what I'll do is I'll create a matrix S, which has as many rows as there are points in x and as many columns as there are points in y. And this is going to be my dynamic programming table. So this is how I'm going to remember all the subproblems. Well, I guess I'll say m, n. So maybe m is the length of x, n is the length of y. So this is my dynamic programming table. So with the Fibonacci, I only needed a one-dimensional array. But here, actually, the dimensionality of my subproblems is 2, because I have all possible subsequences of the first string, and I have all possible subsequences of the second string taken jointly. So I actually need a two-dimensional array. But then otherwise, it's just a matter of going through and well, the base case is just the first row of this matrix, because I have nowhere to go, and the first column. So actually, let me do that first. So the base cases, so the first row is going to be 4j in range n. What I'll say is, actually the very first element is going to be the distance between xi and yj. Let me go ahead and define a distance function too. This is just going to be the Euclidean distance. So that's just going to be, and we'll talk about this more in the next unit, but it's just the square root of the sum of the differences of each coordinate. So anyway, like I said, these have to match the very first point, and they have to match the very last point. So I know that you know, starting off matching the first points, it's going to be just the distance between the two. So it's like I have to match this one to this one. I'm going to pay that distance no matter what. That's the first subproblem. Now I can fill in the rest of the first row, and I can say, all right, S row 0 column j. If I'm following this recurrence, there's only one direction I can go, and that's ij minus 1. So that's going to be s0 j minus 1 plus the distance between x0 and yj. So I should say here x0, y0. So here's the first row. So once I fill in the upper left base case, I can fill in the first row. And now here's the first column. So I'll do for I in range 1 m. Now I'll say si0 is equal to s. So here the only case that I can do is I minus 1 j. So si0 is equal to si minus 1, 0, plus the distance between xi and y0. So those are my base cases. And now I just have to loop through the rest and apply this formula. So now I'll loop through the rest. So let's say for I in range 1 m, and then for j in range 1 n. Let me say sij is equal to min si minus 1j, sij minus 1, and si minus 1, j minus 1. So again, I'm just applying the recurrence here, and based on the order that I'm going through these, I will have computed everything I need by the time I get here. So that is how I would compute the minimum cost. Now, if I actually want to get the solution, so not only the minimum cost, which in this example would be 19.8, not only the minimum cost, but also the minimum solution, so telling you what the warping path is, I have to store one more piece of information here. So what I'll do is I'll make another matrix called, well, let me call it B, because I think that's what I'm going to call it in the next part. So this is a matrix is going to remember the best option. So maybe I'll define some magic numbers here. I'll say that maybe left is 0, up is 1, and diagonal is 2. And so what I'll do here is, actually it looks like up is the first one I did, then left, then diagonal. So let me switch these around. So what I'll do here is, okay, here's my 3 options. And I will actually remember which one of the 3 is the best. So I'll say choices is these 3. I go either up, left, or diagonal to my subproblems, if I'm thinking of how I'm relating through the table here. And so what I'll do is I'll actually remember which one achieves the minimum. And I will store that in this matrix B. And so I will remember the best choice, the best subproblem, but also remember the cost. But ultimately what I'm really interested in is the subproblem. Okay, now I've written enough code, I better run it. So let me quickly grab the Usain Bolt data and I'll try to run this. Okay, so I ran this and I got a little error setting an array element with a sequence. What I meant to say was the square root of the sum of the square differences here. And now I think I'm good. Let me actually just to first check, let me return the cost here. So the problem I'm actually interested in is how to do dynamic time warping for the entire first sequence to the entire second sequence. So let me return the last element, the bottom right corner of this table. And I get 2.0. Now that seems a little bit small, actually, because I forgot to add on the distance. Okay, this is very important. I computed the minimum of the 3 directions, but I'm also supposed to add on the distance. That was the thing I forgot. Classic mistake. So let me also add on the distance between xi and yj. Now I seem to be getting the answer here. So I told you the best warping path was 19.8. Boom, there it is. Okay, nice. So that actually worked. And again, what I was doing was a recursive formulation, but solving it without recursion, actually from the bottom up, always making sure that I had the subproblems that I needed. Now, but the last thing I need to do is actually backtrace through the solution here. So I remember what the best subproblem was. Now what I should do is start at the end and backtrace solution from the end back to the beginning. And that will extract the warping path. So often when we do dynamic programming, we don't just want the optimal cost, the best cost that you could get, but you actually want a solution that achieves it. So this is a bit like when you were solving the rush hour problem, and once you got to the goal state, you actually wanted to see the steps that you took to get there. So what I'll do is I'll start at the bottom right, and I'll say, well, not I equals 0 and j equals 0. What I'll do is I'll follow the best choices that I had. And so my rules here were, okay, up was a 0, so I'll say directions. So if it's up, I'm supposed to subtract 1 from I and stay where I am in j. If it's left, I'm supposed to stay where I am in I and subtract 1 from j. If it's diagonal, then I'm going to subtract 1 from both. So what I'll do is I'll say, okay, based on the choice I made, here's the direction that I need to go. So I'll say my direction is equal to, oh, I guess better not use dir. I'll just say dirij is equal to directions, and wherever the best direction turned out to be, right? So I remembered that here, whichever the best choice was. Now I'll pull it out and I'll say, okay, I plus equals dir ij 0, j plus equals dir ij 1. And I'm sure there's a bunch of ways you could do that, but this is how I'm doing it here. And what I'll do each time I come into this loop is I will append where I am. And at the end, I know I should be appending 0, 0. So let's see what we get here. Well, we get a problem. So let's see, what did I mess up? Well, what I can do to debug this is let's just print out where I am as I'm walking along this. So I started 3, 4, 2, 3, 1, 2, 0, 1. And it looks like I accidentally went too far here. I went up instead of to the left. What I forgot is the base cases that happen in the first row and the first column. So I need to remember, if I'm in the first row, I can only go left. If I'm in the first column, I can only go up. Okay, that fixed it. So the one thing I maybe fix here is because we started at the end and went back to the beginning, this came out of the reverse order, so what I'll do is I'll just reverse it before I return it. But let's compare this, or I can actually plot the warping path here. So if I were to save this to a variable and plot these two sequences, and oops, I need to import matplotlib. Okay, so I import matplotlib, and here's the two sequences. That's me running, that's Usain Bolt. And now what I'll do is I'll just loop through the warping path, and I will plot a correspondence between the two. So I'll take the x-coordinate at I from the first one, the x-coordinate at j for the second one, and then I will plot that against the y-coordinates of each of these. And there we have it. Okay, that looks pretty darn good. So that is, that was a bit breathless, but this was a dynamic programming solution to the dynamic time warping problem. So what I was illustrating here was how you can use a table that you can build from the bottom up, so the smallest subproblems up to what you actually want. I gave you the particular rules for this example here, and I showed that if you build it from the bottom up, so you set up your base cases first, and then you can go ahead and build this up. If you also remember the best subproblem that you had, you can then extract the optimal solution by backtracing. So you start at the end, and then you keep following the best decisions that you made all the way back. And that's that. So that's dynamic programming in a nutshell. I guess I'd probably be remiss if I didn't mention that this can also be used to align audio. I've done a little bit of research on this myself. So I have a web page here about this. I'm not going to play the audio examples because I don't want to get this flagged on YouTube. But if you Google linmdtw, you'll find this. And what you'll see is, so here I took two Vivaldi performances that were playing at different rates. So it's sort of like one Vivaldi piece is running a race and the other Vivaldi piece is running a race. But I want to line them up. And so you can use this to line them up, actually. And it works extremely well. So here we just have to define what it means to have a distance between two audio clips. But so there's a little bit of work to be done there, but otherwise it's the same kind of algorithm. So I love this stuff. I think this is so much fun. This is one of my favorite little algorithms. I hope you enjoyed it too. But regardless, we now have the background that we need to talk about the Viterbi algorithm, which is the next thing we're going to apply to hidden Markov models. So go ahead, look at this, make sure dynamic programming makes sense, because we're going to use it again in another two-dimensional system of subproblems here. Okay, so let's go ahead and proceed to that.